this video, we're going to make use of this standardized development of the conversion formulation from the standard form of quadratics to the vertex form. And mainly the negative b over 2a is the biggie that we want to recall. So let's apply this to a specific example. So here we go. Graph the function 3x squared minus 6x plus 1. Obviously, we know it's quadratic, and obviously the very first thing we should find in here is the most obvious, is the y-intercept, okay? So the y-intercept is nice. It's for picking just x is 0, so the c value over here is the y-intercept. That's nice, okay? Now the axis of symmetry is, of course, the negative b over 2a. It's the same as the x-coordinate of the vertex, which is negative b, which is positive 6 over 2 times 3, which is positive 6 over 6, so that's x equals 1. So the vertex is going to be at x equals 1, and let's evaluate the function at 1. So we get 1 squared 1 times 3 is 3, minus 6 is negative 3, plus 1 is negative 2. So we have the vertex is at 1, negative 2. We have the axis of symmetry at x equals 1. We have the y-intercept at 0, 1. So 1 unit across from the axis of symmetry is the image point. We have this a value is positive, so it's going up. We put it all together, and this is the graph we get. So again, we found the vertex to be at 1, negative 2. The axis of symmetry at x equals 1. The y-intercept at 1. And the image point of that at 2, 1. There's our graph. That's what it entails. In this form, you immediately get the y-intercept. The negative b over 2a gives us the axis of symmetry, and the f of negative b over 2a gives us the vertex, and the a value tells us whether we're opening upward or downward. Okay. This immediately, you should know, has a minimum point because it opens upward. Okay. That's stated down here. Parabola is opening upward when the a in either form is positive. Okay. So now we take a look at some functions which are an offshoot of quadratics. Well, I like to call them quasi-quadratic. So let's just look at it, and then this explanation might be a little bit easier to digest. Okay. So the function we're going to look at is the square root of 2x squared minus 4x plus 4. Okay, so you can see that this is the square root of a quadratic. So effectively, it is a composition of the root function and the quadratic, where the quadratic is the innermost function f of x. So that's what we're going to do. We're going to take a look at this in terms of a function as a composition of a root function with a quadratic. So when we say up here, if f of x is a quadratic and g of x is some variation, a quasi-quadratic, that is, g of x is a composition of some other function with a quadratic, then we can, in some ways, very much treat this as a quadratic. So here, let's take a look. The red graph is the quadratic. The blue graph is the root of the quadratic. You can see that they're both symmetrical on this axis of symmetry, negative b over 2a, or x equals 1 in this case. Okay, so we can take advantage of that and use that to find the low point of this. So this very much, the blue graph, which is the square root of that quadratic, is going to function very much like the quadratic. We're going to find the vertex in the same way. Okay, we're going to find it as negative b over 2a, which is going to be 4 over 4, which is 1, and then f of that. Okay, so that's the same. It's the same treatment given to this. Okay, so here you have it. The axis of symmetry in either the quadratic or the quasi-quadratic is going to be the same formulation. Negative b over 2a and f of negative b over 2a. Okay, so even though you say, oh, I don't know how to graph that, you do, because basically you can still find that low point right there. Let's take a look at another one, if we will. Okay, um, and actually I'm getting a little bit more extra mileage out of this. I said, what if it were the cube root of something? Well, it'd be the same evaluation. Okay, negative b over 2a would be the x coordinate. F of negative b over 2a, which would be the cube root of 2, would be, okay, the corresponding point there. Let's take a look at this, which is another quasi-quadratic. Okay, I'll do a substitution, make it look a little bit more user-friendly. All right, on that front then, okay, we've got the quadratic in P, and of course we should be able to deal with that in terms of finding its vertex, which is going to be negative b over 2a, which is going to be negative 4 over negative 2, which is 2. So we've got that, okay? But remembering that is the x coordinate of the vertex, but since that was actually, since p was in for x squared, then we have to say that the x coordinate is going to be both positive and negative 2, going by back substitution, what we had there. Okay, so substituting these positive and negative roots back up in here will give us the same y value because it has symmetry. So we got, throwing in root 2 to the 4th power. Root 2 squared is 2, squared is 4, and that's a negative 4, and doing all the algebra that goes along with that, we find that we have actually two vertex points. So it's not really a vertex point, but it's 2 high points on the parabola. The y-intercept is 12, and look at the graph, okay? Here it is, okay? Here's the y-intercept. Here's the radical 2, 16. Here's the negative radical 2, 16. We already know, at least we should recall, that this function had symmetry just by the even powers of x, okay? We temporarily treated it quadratically so we could find out that the vertex in terms of p was at 2. But back substitution of p being x squared being 2 means that x is actually going to be the root of that, which again is going to give us these 2 points. This is a classic shape of a 4th degree polynomial. It's kind of an M shape. Clearly shows the symmetry, okay, and basically that's a nice easy way of graphing a function of that sort, okay. Here's a quadratic regression model, okay. As a follow-up, this is one of the problems out of the book. Okay, got all this information for the consumption in billions of tons of coal over years beginning 1990 is year 0, 91, 92, 93, 94, 95. I think they ask us in this problem to find the what would have been the consumption in the year 1989. So we have to get our regression model of a quadratic nature. It seems to be a pretty nice fit. If you can't recall how to find that, then go back and review my videos on linear and quadratic regression, okay? And from the table, we set the table value to ask, and we ask for the 1989, which would be year -1. And according to that, the model predicts the consumption would have been 3.46 billion tons. Okay, so that should do it for this. Okay.